couple times, but the most recent title was gigawatts. It was something like this: gigawatts of energy in every cubic inch of space surrounding circuit wires. Gigawatts, right? I think that's billions of watts. And that's, we can look at that as watt hours, but it's also watt seconds, which is joules. So that's 60 times 60, right? 60 minutes in an hour times 60 seconds in a minute. That's a lot of billions of watts, watt seconds. The reason I'm sharing this video at this moment right now, what I'm thinking about is, I realized in watching my last video, even though it's accurate to say that there's billions of watts of watt seconds and watt hours both, and even watt seconds times watt hours. I guess you could multiply those two and you'd still have, I mean, we're really talking about all the energy in the universe, right? Because all energy, all subatomic particles are interacting with the zero-point field, which is the source field of all energy, which sustains the material universe. And the material universe sustains the zero-point field. How amazing is that? Because one of my first questions were, what powers the zero-point field? Oh, the material universe powers the zero-point field, right? Okay, so to share what I'm thinking about at the moment is, I realized in watching my video, this is why it's so helpful to make videos and to look back at them. I thought to myself, what was I thinking when I said we could use the wires going from the controller to the motor? Where did that come from? I actually have no idea where that came from. Did I dream that? Was that a dream, or was that just an experiment I want to try? And I know I've tried that experiment before with circuits, and I don't know if I know what I was looking for, but I certainly wrote down what I saw, the results. And it's important to consider that. What are we looking for, right? What are we looking to notice when we are doing an experiment? And a lot of the masters of the universe, if I say it that way, right? Masters of the universe, masters of energy, that have studied this for generations and entire lifetimes, say that be very open to what you notice. This is a paraphrasing, right? To an approximation of what was said. To notice what is taking place, because most often something can be happening that is not what we anticipate, not what we're looking for, right? For example, let's say we're trying to charge a battery. Let's say we're trying to charge the same battery, right? Because there's two ways we can charge a battery in a circuit. We can charge the battery that's powering the circuit, or we can charge a battery that's separate from the circuit and it's just being charged, but no energy is being taken from it. So let's say we're charging a battery that is powering the circuit, right? Which is said to be many times less efficient, right? So it's more efficient to charge a battery that's not powering the circuit. And that can be different for different batteries, for different chemistry batteries, right? So that might be different for a lead acid battery versus a battery that is lithium ion or lithium iron phosphate. It could be different for any different battery, right? So these are all different tests that can be done. I'm interested in conducting those tests and noting the results. Today I'm sharing my thoughts with you. That's what I always do, is share my thoughts with you. And I thank you for sharing your thoughts, your experiments. So what I want to share with you is a thought about what happens when we have coils with iron cores. those iron cores could be welding rods, and I think they need to be welding rods that are a ferrous metal where a magnet can stick to them, right? And there's particular welding rods that are better than others. But it could also possibly be, for this purpose of my experiment that I'm talking about right now, it could possibly be a solid iron metal rod. So instead of little thin sticks of metal, like 1/16 of an inch, it can be maybe a 1/4 inch ferrous metal, meaning a magnet can stick to it, rod, and that would be in the center of a coil, right? And the coil would be, I think it's called magnet wire. I think that's one of the words used for it, which is something that we want to use when we want to generate energy, right? I'm just using words such as generate, but what's actually happening is, from what I understand, and this is what I think is happening, is we're pulsing. So that iron is non-polarized. I'm going to say it that way. It's non-polarized, and then when a magnet passes the iron becomes polarized. And in the instant that magnetic field, in the instant that iron depolarizes, there's an impulse, if I understand correctly, and please study this for yourself in studying Nikola Tesla impulse technology. When the iron core of a coil becomes depolarized, which is when the magnet interacting with that iron core leaves the proximity of that iron core, there's an impulse sent out into the environment. An impulse. That impulse strikes the coils that are wrapped around the close proximity of the iron core, the ferrous metal, that is just depolarized as the magnet left its proximity, left its area. The coil, the copper wire coil, anywhere from 23 gauge to 26 gauge, but I'm interested in experimenting with different gauge wires. But those are some gauges that I have read of that are popular, but usually in reference to using a motor generator system in one, if we think of John Bedini. I'm interested in separating the experiment into two separate parts, or two separate systems, which is a generator system in one area and a motor system in a different area. So the prime mover, or the motor, will be whatever is driving the electric system, which includes the battery that is part of that circuit. We'll call it battery A. One of my interests is to charge battery A, which is the battery that's powering the circuit. What we'll call battery B would be a battery that is separate from the circuit and being charged without being discharged simultaneously, but just being charged, right? There's also theory and practice of discharging a battery in pulses, and between the pulses of discharge to charge that same battery, and that's supposed to be more efficient than continuously discharging and continuously charging battery A, or the same battery that powers a circuit. So if we have battery A powering the circuit, powering the motor, the prime mover that causes the motion, whatever's moving, right? A wheel, we'll say a wheel. Some kind of wheel, it could be any wheel. And then if we say this wheel, Okay, for the moment, I'll say this wheel is for the moment, I'll say that this wheel has magnets on it that are going to pulse they're going to give us our impulse signal. They're going to give us they're going to pass a coil with a ferrous iron core. And when that coil is impulsed, if I say it that way, when it's impulsed from the depolarization of the ferrous iron core, it pushes against the environment where the megawatts of potential energy, right? We can call it energy or potential energy. It's energy, but we have to use it. When we use it, that's when it becomes more than potential, right? But we have billions of watt seconds in every inch of space. And it's actually all the energy in the universe, so it's much more than that. We're just using small numbers. When we say billion, we're actually just using small numbers. But in actuality, there's infinite energy in every inch of space, or we could also say that every subatomic particle has access to all the energy in the universe and all the energy in the zero-point field, including all the energy in the material universe, right? Okay. These are all thought experiments based on research and study of hundreds of thousands of books on science and what we know and what we think we do not know. If I say it that way, right? What we think we do not know, right? So, when we impulse a coil, and that coil, if we say it this way, when it interacts with the environment, like water pressure, if we think of it that way, the environment the energy in the environment, we could say it this way, is translated from potential into actual, right? From potential energy to actual energy, which actual is just like, if we think of amps and volts, right? And we can talk about what is an amp and what is a volt, but right now we're going to just focus on this idea of the impulse, right? Nikola Tesla impulse technology, right? And this is my thoughts on it. And I'm still learning, and I'll always be learning. So, when the coil receives an impulse from the depolarization of the ferrous iron core, when the copper coil sends an impulse signal to the environment, the ambient energy, right? Which is all the potential energy in the universe, zero-point field and material universe combined. That coil, let me think about this now. That coil, what I would like to do is connect that coil. It's going to have two ends, right? Two wires, because a coil has two wires, right? One wire at each side of each end of the coil. Connect that coil to a full wave bridge rectifier, and then to a battery, and then watching the voltage of the battery and watching the temperature of the battery. Never allowing the temperature to go higher than is determined safe for that battery, whatever battery that is, whatever chemistry battery that is, and whatever specific battery that is. And also not going higher in voltage than the battery is rated for. With lead acid batteries, it's common in experimentation for people to go above the voltage, above the whatever it may be, 13 volts, 14 volts, or even up to 15 or 16 volts with lead acid batteries. I've seen this in experimentation of people doing this. I've done it myself. What I always watch for is the temperature. If the battery's getting hot, I'm not going to do it. I'm going to stop. But if the battery's staying cool or cold, I will allow the voltage to go to 16 volts. I don't go beyond that, even though I've read that some people have gone far beyond that. I think even up to 40 volts with a lead acid battery, a 12 volt lead acid battery. I'm not interested in doing that at this time. And if I was going to do that, I would watch the temperature of the battery and make sure it's also not boiling. Some people say there's a cold boil that can take place, where the battery stays cold, but it can make bubbles. I don't know what those bubbles are. Are they hydrogen? What are they, right? Because that could be dangerous too. We have to be careful, right, with sparks. So these are all considerations in safety. Okay, now something interesting about this experiment that I'm discussing right now, that I'm sharing actually, is we have this coil charging battery A, which is the circuit battery, right? What is the voltage doing of the battery? Because the battery is powering a prime mover. Are we able to slow the decrease of voltage compared to if the battery was not being charged with the impulse circuit, if I call it that? Very simple impulse circuit, right? Minimalistic circuit, minimalism. Ferrous iron core, coil wrapped around that ferrous iron core, magnet passing the ferrous iron core. It is important, I think, well, this might be more for the motor and generator combined to have the magnet spaced out, but I do think that the spacing of magnets, how often a magnet passes that ferrous iron core, is important. It doesn't seem to me like we want continuous magnetic field or continuous polarization. Although I do wonder at this moment if the polarization was switching from, let's say we use all north poles passing that ferrous iron core. If all the magnetic fields passing that ferrous iron core of the coil in our generator, if I call it that, it's really a translator. A lot of people call it a pump, an energy pump, pumping energy from the environment into the circuit as desired. But it's really, I actually see it as more as a translator of energy, or a coherence of energy, cohering ambient energy, right? That's one way of thinking about it, that I'm thinking about it. So, let me see. So there's different tests that could be done. Let's say if we're going to have, I would think that I would do these tests with some spacing between the magnetic fields. So the two ways it can be done, let's say we have 3 or 4 inches between the magnets, right, on a wheel that's passing this ferrous iron core. So 3 to 4 inches, maybe 4 to 5 inches between each magnet. Giving the polarized and depolarization process of the ferrous iron core time to depolarize completely, right? Allowing time for ambient energy to activate, if I say it that way, the circuit or the battery, right? Because some of the ways I've read of this energy moving through space is in theory, if we study Dirac holes, D-I-R-A-C, that the electrons are shaken directly loose from the Dirac holes and are placed directly into the battery plates or the battery ions. Somewhere in the battery, right? Somewhere in the battery, the electrons go straight there. Which is why when measuring battery capacity, it's important to discharge the battery in these kind of experiments and see how much capacity is in the battery once it's been charged in this manner. My interest is less at the moment in testing battery capacity and more in just seeing what voltage does as the circuit is running. So if I'm discharging battery A, powering the circuit, and simultaneously charging battery A with these impulses, right? Is my voltage decreasing slower than it would if I wasn't charging the battery? So it's acting as a range extender, right? Or is the voltage even staying the same or increasing? And there's a couple different tests that can also be done. My research and study indicate that we can also notice that keeping a battery fully charged is different than charging a battery that's almost completely drained. So if our circuit battery, if we drain our circuit battery to almost empty, whatever chemistry it may be, right? And then we run our circuit and see if we can get the voltage to go up, right? Charge the battery, which many engineering students have practiced this experiment, this kind of approach with their self-charging electric cars and self-charging electric motorcycles. Many engineering students have collaborate with this kind of circuit with their teachers in colleges. This information is all freely available on the internet and in books as well. What's important is doing the experiment, right? Learning from others. What can we do differently than what has been done before? And how can we replicate successful experiments? And how can we take two different successful experiments and combine them or modify one or both of them to complement one another, to make something new, possibly more efficient or just different or less parts, or maybe more parts, but parts that are easier to get. But so far, what we're discussing so far, and thus far, is, as I understand it, are easily and readily available parts from the hardware store, and using, ferrous, using magnets that are can be ordinary magnets, like refrigerator magnets that stick to the refrigerator, or they can be neodymium magnets. That's my understanding, that just leaving that space between the magnets is important, though. And that 3 to 4 inches, right, approximately. And then trying it both ways, trying it with all norths facing the ferrous iron core on the coils, and then trying it north-south, 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 and then trying all south. We can try it both ways. But the main two would be just trying all norths, and then all north-south, 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 and then seeing if there's a difference, seeing how the battery reacts or responds differently to that. And then also, after doing all this testing, also doing a separate test where we now take the two wires coming out of the coils, each coil, that was going into a bridge rectifier, a full wave bridge rectifier, converting that AC pulse into a DC impulse, right? And instead of going to battery A, which is a circuit powering battery, go to battery B, which is a battery that's totally separate from the circuit, that is not being discharged. Okay, everyone. Thank you for being here today. Thank you for sharing this journey on Spaceship Earth. And I look forward to hearing your thoughts in your videos. continue learning and continue being inspired. Have a great day. Bye, everyone.